There we go. Okay, cool. So everybody good with that? Is that a question, Ethan? You just okay. All right. Oh, that was my drawing from yesterday. Okay, so torque and Newton's second law. You ready? I hope not. My honors class has a test on it tomorrow, and they were struggling at the beginning, but I think everything kind of clicked in the last couple of days, so I think this won't be too bad. All right, so here's the deal. Short explanation of torque, and then we'll get into more detail. All right, so this whole chapter is about learning about sort of the rotational counterparts to everything we learned in the first chunk, right? All the kinematic stuff, right? So we learned about linear velocity. Now we're doing angular velocity. Linear acceleration, angular acceleration, right? So at the beginning of the year, after we learned about acceleration, the next thing we talked about was force, right? Because force causes acceleration. Okay? So torque is sort of the rotational counterpart to force. Okay? In the same way that you need a force to change the velocity of an object, you need a torque to change the angular velocity of an object. Okay? So somewhere I have a wheel. Here it is. All right? So right now this has an angular velocity of 0. All right? And in order to change the angular velocity of this, I need a torque. Okay? So that torque, first of all, to have a torque, you have to have a force. But not every force produces torque. Okay? For example, it would be possible for me to push the wheel, but not produce torque. Okay? So the torque turns out that it's dependent on a few things. How much torque there is dependent on how much force is exerted, how far it is from some pivot point. For the wheel, the most obvious pivot point would be the axis of its rotation. Okay? So the torque depends on how much force you're exerting, trying to change the rotation. How far the force is going to be applied at some point. Okay? So the distance between your pivot point and where the force is applied is important. Okay? And then also the direction of the force is important. Okay? The reason this doesn't produce torque is because of the direction. If I want to produce torque, I need to change the direction of my force to be either downish or upish. Cool? All right. So, I guess let's talk about those things. So, if you go open that door over there, all right, assuming that somebody's already turned the doorknob, right, so you don't need to worry about the latch. Obviously, the harder you push the door, the faster it's going to open, right? Okay, so more force produces more torque. Okay, that's definitely important. Obviously, the direction that you push the door is going to matter, right? Like if you go. I know, it hates me. So if I want to cause this to rotate, pushing this way isn't going to do anything, is it? Right? Like, right? Okay, the direction of my force matters. I got to push this way or this way, right? Okay? And then finally, I wish these doors swung in. They don't, but you've all done this. You're like not paying attention to what you're doing. You walk into the mall and you go to push a door open that you're supposed to push open, but you push the wrong side of the door. Oh, yeah. Right? And it sucks, right? Because what happens is the force is being applied at a very short distance away from your pivot point, so all of that force doesn't provide much torque. That's why they put the doorknob at the outside edge of the door, right? Does that make sense? Okay? So, there are 3 things that determine your torque, and then I'll get your question. I didn't know if you had a question. Oh, did you really? Sucks, doesn't it? Right, so, here's the equation for torque. It's the cross product of, we'll review that, it's the cross product of R, which is the length of what's called your lever arm. In English, it's how far it is from your pivot point to where the force is applied. So it's the cross product of that vector and your force vector. All right? When we did cross products, we learned that you can calculate the magnitude of your cross product by doing the magnitude of your 2 vectors times the sine of the angle between them. Okay? So, I think probably the easiest way to do this is to just jump in and do a couple examples. Also, I just realized I used to use D, and I'm trying to use R this year, because it's what's in your book, and I forgot to change this here. So that should be an R right there.
Wait, so what is?
there's not a better answer for it than to say that it's the rotational counterpart to force. It's what, in the same way that force changes how quickly an object is moving linearly, changes the velocity of an object, torque changes the angular velocity of an object. So as a couple simple examples, so this is spinning right now, right? If I want to change how quickly it's spinning, I need to produce a torque. So I can either add to how quickly it's spinning.
So so you just increase this torque?
I increased its angular velocity. Using torque. Me pushing it was the torque.
Torque is a force.
It's a result of a force.
So torque is okay. So you need a force to have torque, but torque is a force. It's a result. Also
Yes. Yes. Let's do a couple examples, and I think you'll see, once we do a couple of calculations, it'll make a little bit of sense. But let me say this. So in the same way that an object will accelerate linearly while it has a net force on it, Alex, an object will accelerate angularly while it has a net torque on it. Okay? So when you hit the brakes on your car, you're putting a torque on your wheels to change how quickly they spin.
Okay.
When you push the gas pedal, you're putting a torque on the wheels to make them spin faster. When you use a wrench, which this is an example we're going to do in just a second,
Yeah.
when you use a wrench to turn a bolt or a nut, you're producing torque and changing how quickly the bolt or nut is turning.
Okay.
So the force produces a torque which changes the velocity. Angular velocity.
Correct. So that was said perfectly. She said the force produces a torque which changes the angular velocity. Yes.
The torque do any work?
Torque can totally do work, and we'll get that. Because you're changing your angular velocity, therefore changing your kinetic energy.
Yeah.
Sorry, David and Ethan. David.
So you said braking, so friction, friction level that was like torque.
Yeah, so just today in my honors class we did a problem about, how 10 speeds have brakes that do this,
Yeah.
right? That's applying a torque to the wheels to change how quickly they spin. In a car it's similar, it's a little more complicated because of the way the brakes in the car work, but same basic idea.
And what's the unit for torque?
Newton meters, we'll get there in a second. Because it's meters cross, right? So in non-metric we use foot pounds, we're going to use Newton meters. Cool, and I'll talk about that in 1 second. Yeah, Ethan.
Is that angular velocity times radius would be linear?
I gotcha. I never thought of it that way. Not really, because those jumper equations just give you... No, it's not the exact thing. I know what you're saying. I don't know if I would think about it that way. Largely because most of the jumper equations are linear equals angular times radius, and this one's actually the other way around.
Right.
So I guess I'd be careful thinking about it that way. This is more, it's a definition. This is what produces torque. A force applied to an object at some distance away from the pivot point. Cool?
Isn't the torque always perpendicular to the force force?
Yeah. Because it's a cross product. Remember, the cross product is always perpendicular to the two vectors. Okay, so we're going to get to right-hand rule. We got to use the right-hand rule here, okay? All right. So, I think this will be made easier once we jump into an example. Does anybody have any questions that can't wait until we do an example or two?
Yeah, what letter is that here?
Oh, it's the Greek letter tau, and I usually write it as a T with a wavy top. Is usually how people draw it. Okay, Greek letter tau stands for torque. And notice the way that I draw it and the way it gets typed by stupid Microsoft is different. Okay, so cool. And this is the way people usually draw it. So that's not just me having crappy handwriting. Yes. All right, everybody good? All right, so here we go. So let's take a look at a simple example with a wrench, okay? So the idea here is presumably our wrench is trying to loosen some sort of bolt or nut or whatever. So we'll get a little hex nut there, and then there's, a screw or whatever in the middle. All right, so the idea is when you talk about torque, the first thing you have to establish is what's your pivot point? What's your axis of rotation? All right, on a door, the axis of rotation is the hinges, right? If you spin a basketball on your hand, then the axis of rotation is the axis running through the middle of the basketball, right? Okay, on a wheel, it's the axle of the wheel. Okay? Here, this is going to be my axis of rotation. I will usually mark it with a P to indicate pivot point. That's the point that it's going to pivot about. Okay? Now, if I want to make this wrench rotate, I need to somehow produce a torque. And to get that torque, I need a force. Okay? So, first of all, let's talk about some things that will not produce torque. Okay? Would pushing right here, let's call this F1, would that produce a torque? No, that's like pushing on the hinges trying to open the door, right? So in general, so this is F1, so I'm going to write the corresponding torque for that as torque 1. So torque 1 would be R1, I guess we call it, cross F1, right? And the idea is, what's my radius here, you guys? 0, right? So this just becomes 0 cross whatever F1 is, and it's 0, right? Because your lever arm has a length of 0. Good? All right, now, another way to do it, what if I push down here? We'll call this F2. Same thing, right? But, so there's a couple ways of thinking about this. Technically, my lever arm isn't 0 anymore, right? So this distance here would be my lever arm. Okay, the lever arm is defined as the vector that points from your point of rotation, your pivot point, to the point where the force is applied, right? But what's the angle between my lever arm and my force? 180, right? So I'm going to have RF times the sine of 180. That's going to give me 0 also, right? So torque 2 is R2 cross F2. Does everybody understand this notation that I'm sort of making up here? Okay. So this is the same as R2 times F2 times the sine of, I guess we'll call it theta 2, is R2 times F2 times the sine of 180, and the sine of 180 is just 0 because of that. Good? So, if I want this wrench to rotate, which way should I push? Either up or down, right? Depending on whether I'm trying to do righty-tighty or lefty-loosey, right? Okay? So whether I want to tighten it or loosen it, right? So, suppose I push down here. We'll call this F3. This time we'll actually pick a number. Maybe it's, I don't know, whatever. We'll just do 10 newtons. That way the math will be easier. Okay? So now I can do torque 3. Well, that's, notice my R is still the same as it was in R2, right? So this is going to be R2 cross, R3 cross F3, which is the same as R3 F3 times the sine of what? 90 degrees. What's the sine of 90, you guys? 1, right? So a lot of times in the homework, your angle is going to be 90 degrees. All right? You will very often see in books torque equals FD. That's only true if the angle between your force and your lever arm is 90. Follow? But it'll happen often. So eventually I'll probably just start writing torque equals FD, and that's what that means. You're just assuming that your lever arm and your force are perpendicular and everything works out friendly. Cool? All right. So for us, well, let's see, we need to measure this, right? So I grabbed this little thing here. So let's see. Oh, well, that's weird. So our distance happens to be 0.1 meters. That's annoying. So we're going to have 0.1 meters times my force, which I foolishly chose to be 10 newtons. So you multiply it, we're going to get 1 newton meter, right? Oops, 1 newton meter. Cool, you guys? Any problems? All right. So notice that for that amount of force, that's the most torque I could possibly get, right? Because my sine of theta will never be bigger than 1, and my force is all the way as far away from the pivot point as it can be, right? So for this situation, that's the maximum torque I can produce using that force. Good? Okay. So what are ways I could decrease the torque? Well, there's three ways. Decrease the force, decrease the radius, or change the angle. Good? All right, so let's do all three of those things just so that we can at least once have done a full calculation like that. And then we'll move on. All right, so suppose I have F4. Let's make it be 8 newtons. And suppose I told you that this angle here is, I don't know, let's just do 30 degrees because that way the math will be easy. Cool? All right, so it looks like my distance now is 0.08. That's annoying that I keep picking the same numbers. All right, so here we go. So last one, torque 4 is radius 4 cross force 4, which is R4 times force 4 times the sine of my angle. So our radius was 0.08 meters. Our force is 8 newtons times the sine of 30 degrees, right? Good? So I believe that that gives you 0.32 newton meters, if I am not mistaken. All right, so this torque is significantly less than this one because we decreased all three values that determine the torque, right? I made my lever arm less, I used less force, and I didn't maximize the angle by using 90 degrees. Make sense? All right. Now, direction. So, when you use this, when you use RF sine theta, that gives you the magnitude of the torque, but it doesn't tell you the direction of the torque. Okay? So to determine the direction of the torque, you got to use the right-hand rule. Okay? So I'm going to show you the way that I learned the right-hand rule, and I know you guys have this thing. I always get the fingers in the wrong spot. I've never seen it this way before. Is this right?
Yeah.
Yeah? Okay. I'm trying not to flip you off, because I know that's a thing. Right? Right. Okay. So if you know this thing and are comfortable with it and can use it, then awesome, and I'll just assume you're not giving me the burden. Okay? Here's how I do it. Okay? When you do a cross product, what you do is you line your hand up, your right hand, you line your right hand up to point along the first vector. So for me, I'm going to line my right hand so that the fingers point along the direction of R, my lever arm, and then you curl your fingers in the direction of the second vector. So, let's see. I want to get a new drawing here. So we've got this. So on all of these, we had a force that was downish, right? In some sense, the force was down, right? Okay, and here's my R, right? So what I want to do is I want to take my right hand and point my fingers in the direction of R, and then curl my fingers in the direction of F, and see which way your thumb is pointing. So for me, it's pointing into the board, which indicates negative z-axis. All right? So that one was pretty easy. But suppose that I instead had my force up. My fingers don't bend that way, so what do you have to do? Right? Because you can't bend your fingers backwards, so you got to turn your hand over and then curl your fingers.
Wait. Hold on.
For magnetic field, yep. Yeah, it's the same thing you do for magnetic fields. All right? So, if you like the finger thing better and you know how that works, great.
It's okay.
And sure, I get it. That's what you guys should put on your shirts. Right. All right, so that's how you do it. So if your thumb points out of the page, that's positive because it's like pointing up out of the z-axis. And if your thumb points into the page, then that's negative. Okay? Notation. Well, okay, so before I get there, so that works. Okay? The other way to do it is to still use what I was saying before, which is this. Look, this one's going to point out of the page. That's counterclockwise, right? And we decided that counterclockwise was positive, right? And then this one points into the page. It's negative. It's clockwise. Clockwise is negative. Okay? On the chapter 10 homework, in my head, the whole time, I just did clockwise, counterclockwise. I don't know if I ever had to use the right-hand rule in chapter 10. I might be wrong on that, but
Wait, so will that always be right?
as long as everybody's looking at it from the same direction, yes.
Okay.
Okay, so,
All right, so here, let me make it so they correspond. So does that help?
yeah.
So the green corresponds to the green.
Yeah.
Everybody good? All right. I was going to say one other thing about that. Oh, here's the other thing. Sometimes you'll have to draw the direction of the torque, and if it points into the page, you draw this. Have you seen this before? And this is out of page, right? So it's like an arrow, right? Here's you looking down the shaft of an arrow, right? Here's the point, and here's you looking at the tail feathers. The arrow's going away from you. So you've seen that before?
Yeah.
Okay. So there will be a couple times, like on the homework, I think there was one problem in one of the chapters where I used this as my answer, you know, as what direction, and I just drew this. So, cool?
Yeah.
All right, questions on all of this? Okay, so that's how we produce torque, and hopefully it makes some sense, right? Because if I want this wheel to spin as fast as possible, pushing, so when I push right here, where's my lever arm? It's this spoke, right? Okay, and so here my angle is 180, right? That's why it's no torque, right? So to make the wheel spin as fast as possible, I want to put my force on the outside edge, right? And I want it to be perpendicular to the spoke that I'm pushing at. Cool. All right, any questions about?
I have a question.
Yeah.
Okay, so if you have a constant force acting on a wheel, it's like X on time, will that be like a constant increase in torque?
Yes, if by constant you mean constant such that the angle between the force and the lever arm are constant, right? Like if this is a door
Yeah.
and this is my force,
Yeah, like that's what I'm saying.
then yes. Yeah, that, so constant force will produce constant torque, which will produce constant angular acceleration.
Torque?
Yeah, because your force and your lever arm would be the same the whole way around, right?
Yeah, but wouldn't it be an increasing angular velocity?
Yep. So that's the same as saying a constant force gives you increasing linear velocity. Constant torque gives you increasing angular velocity.
Wait, constant force gives you increasing
Velocity.
Acceleration.
Basically, the torque is force.
No, but you understand, like force produces acceleration, right?
Yeah, yeah, but you said, I think I'm just confused, because you said torque produces, never mind, I got it.
You sure?
Yes. Yes.
Okay. Okay. All right. So, where's my doohickey? Yeah. Oh, there it is.
Is the direction of torque the same direction of angular acceleration?
Yes. Real. Oh wait. Yeah, that's true. Not necessarily angular velocity, just because, for the same reason that linear acceleration and linear velocity aren't always the same, right? So, but your question is a really good one. It's probably something I should have commented on, which is this. In the same way that your net force and your acceleration are always in the same direction, right? Because net force equals mass times acceleration. In a minute, we're going to see that your net torque and your angular acceleration are also in the same direction. Olive?
Wait, are angular acceleration and radial acceleration?
Yeah. Oh, ooh. No. No. So there's three types of acceleration.
There's tangential.
Tangential and radial, those are both linear, like they would be meters per second squared.
And then angular.
And then angular. Exactly. Yeah, Alex. Exactly, yeah. Because it's either clockwise or counterclockwise, but really when you do the right-hand rule, that's either into board or out of board. Make sense?
Wait, so when you're spinning a wheel, the angular acceleration is on the edge.
Yeah, here, okay, so, all right, so let's go back to the right-hand rule. So let's do this. So for a minute, let's assume this is spinning at a constant velocity. Use the right-hand rule and tell me which way the angular velocity vector points. Use the right-hand rule and tell me which way the angular velocity points. So I'm going to curl my fingers in the direction of rotation. My thumb is pointing at me, so it must point that way. So the angular velocity is that way, towards the wall. Does that make sense?
That's angular velocity.
That's angular velocity. All right, now, I'm going to slow it down by providing a torque. What direction was the torque that I just created?
This way.
Let's see, here was my lever arm, the force was up. So let's see, right hand lever arm, force was up. So the torque was that way. Which makes sense, because look, it was spinning this way, and I slowed it down by pushing it that way. Right? So the angular velocity and the angular acceleration are in opposite directions. They work against each other.
That makes sense.
Good?
Wait, so. Okay. Sorry. That's
No, don't be. This is good. I didn't know how much of this you guys had had. So, are we making sense? Are we good?
Wait, so. Does torque and angular acceleration always move in the same direction?
Yep. In the same way that force and linear acceleration always go in the same direction.
Okay.
Good?
So you can almost think of like angular, like force and velocity and acceleration as like linear on the axis.
Yeah.
Because it's like a velocity specific.
Exactly. 100% you can. 100%. Okay, good? All right, cool. I hope that was a helpful discussion. I hope we'll get through everything we need to, but that's okay. Just want to make sure you understand it. So, everybody good?
Yes.
No, you're good. Alex, I'm glad you're asking questions. I wish. All right, now, because torque is a cross product, sometimes you're going to get problems that are in stupid unit vector notation, which means we got to take a minute and review how to do cross products. Okay?
Isn't that object?
It's the IJK thing, and I'm going to use the Mary Shepard Secret Ninja trick that she showed, because I think that's the easiest way to do it. I hope you don't mind that I just named it after you, Mary. Where did I put my notes? What's that? Oh, right. Okay, so imagine a scenario in which we had a force of negative 2I minus 3J plus 5K newtons being applied to some particle or object or whatever, so that, I guess I should have put a little, so that your lever arm, your R, is this vector, 3I minus 4J plus 2K meters. Sure, yeah, that's just pointing away from, so I'm assuming my pivot point is at the origin. So in 3 dimensions, here, oh, pretend that hit. There's my pivot point, right? And then my particle's out here somewhere in space. That vector describes this. Cool? So my particle's here, and then my force is coming in at some weird angle, and it's going to cause it to rotate around this origin. Yeah, so, it might be doing like one of these, or, I don't know. Good? All right, so when I find my torque, what I'm doing is the direction that the torque points in defines the axis about which it's rotating, right? Right, does that make sense? Like when I spin this wheel, right-hand rule gives me this, and my thumb is pointing in a direction parallel to the axis of rotation, right? Okay. Okay, so here we go. So we got to do R cross F. Remember, with cross products, the order matters. R cross F is not the same as F cross R. Okay, so you have to do it in the right order. All right, so if you have a way of doing these cross products that works, great. I don't think this is the way that I taught you guys at the beginning of the year, but I think partway through the chapter I showed you guys this trick that Mary showed me, and I like it, so I'm going to stick with it. So what you do is you write out both of your vectors. You do the first one first. So I'm just going to write out the components. So 3, negative 4, 2, and then you do it again. 3, negative 4, 2. Did I show you guys this or no? Yeah? Okay. I thought so. All right. And then you're going to do the same thing with your second vector. You write it below. So negative 2, negative 3, 5. Oh, shoot. I wanted to write those in black. Oh, well. Negative 2, negative 3, 5. And again, technically, you guys, what this process is basically doing is you're just foiling this out. Okay? But this is just like a way that does it systematically, and you don't need to worry about, well, let's see, I times j is this, but j times I is that. This just always works. So thank you for sharing. Okay, so what you're going to do is you're going to start, so this is ijk, right? So I is here. So remember, j cross k is I, or k cross j is I. I don't remember which one off the top of my head. But so I'm going to do this and this, and that's going to give me my I term. So it's negative 4 times 5 is negative 20. And then you do minus these guys. So negative 20 minus negative 6 is negative 14. That's my I component.
So that probably should be like.
Yep, it's always,
Give the guy.
yes, correct. So the red ones that I just drew there give you the I. So it's always this minus this. Like finding the determinant of a 2x2 matrix. It's basically what we're doing here. Good? In fact, that's exactly what we're doing here. Good? All right, and then you just move down. You move down a spot. So this one and this one is going to give me the j component. So 2 times negative 2 is negative 4. Minus 15 is negative 19. J. Follow? And then move down to the next one. So these ones are going to give me the k's. So let's see, negative 9 minus 8 is negative 17. All right? Okay. And then my units are Newton meters. Good, you guys? Not that this helps you guys any, but I think next year I probably won't even teach cross product until we get to this chapter, because you guys have had like 3 months to forget all this. So I'll probably just push it back next year. All right. Does this ring a bell though, vaguely?
Yeah.
And again, if you've got a different method for doing your cross products, then more power to you. Awesome. Okay. As long as you can do it and get the right answer, then we're all happy. Good? Everybody good? Mickey, you good?
Yeah.
I don't believe you. What's up?
I was just, you didn't use the first two in the last two.
I gotcha. So they sort of got used here, right? The 3 and the 2 get used here, and the 2 and the 5 get used here. The quick explanation for it is this is the I column,
Right.
and when you do unit vector multiplication, j cross k is I, so that's this, and then k cross j is negative I. Cool. So that's where the minus comes from.
It's been a while since
And is it I cross I 0?
Exactly, which is why you don't need to use this for exactly. All right, cool, you guys. All right, excellent. So that is how you do unit vector notation. All right, so Newton's second law tells us that an object's linear acceleration depends on the net force on the object and on the mass, right? In other words, acceleration is net force over mass, or net force is mass times acceleration, right? That's Newton's second law. All right. Now, yesterday we spent all this time talking about rotational inertia. I think that this was all in your slide yesterday, and I included it again just because I thought it was relevant again. But so all we're going to do is we're going to rewrite Newton's second law for our torque values. So acceleration becomes alpha, angular acceleration, right, is now equal to not net force, but net torque divided by not mass, but rotational inertia. Okay? In other words, the rate at which an object accelerates angularly is proportional to the amount of torque that you're putting on it, and inversely proportional to its resistance to a change in rotation. Cool? So it's literally the exact same as Newton's second law, except that you're dealing with rotation instead of linear motion.
Wait,
Okay? And the way, let me say this one last thing and I'll get you. Usually the way this is written is this, that net torque equals I alpha, in the same way that usually Newton's second law is written F equals I. What'd you start asking?
So rotational inertia is basically just like rotational mass.
It's 100% left rotational mass. Yeah, that's a perfect way to think about it. All right, so this just all says stuff we talked about yesterday, that the rotational inertia depends on the mass, the size and shape, and the axis of rotation. Good? Any questions? All right, so here, if you care, is a quick derivation for why net torque equals I alpha. I'm just going to kind of plow through it because I don't know that it's that instructive. But so, no, I guess I probably should talk about this real quick. Nuts. This took longer than I thought it would. All right, so I got to take a quick step back to explain one thing real fast. I want to make sure you understand what this little T is here for. It's a weird notational thing. So, in that example I did a minute ago, we had this wrench, right? Wrench. There we go. Cool. And here was the nut, right? Okay. So, suppose that I think I did an example where I pushed on it this way, right? And we said you could find the torque by doing FD sine theta. What does the sine theta really represent, though? If this angle here is 30 degrees, and I do F sine theta, isn't that just giving me this component, the component of the force that's perpendicular to my lever arm?
Yeah.
Cool. And so the idea is that force is going to be tangent to the path that this point follows. Okay? So this force is, I don't know that you'll see this notation that often, but it does come up. So this force is exactly that. It's the component of the force that's tangent to the circle that that point is going to follow. I've also seen it called F perpendicular, as in perpendicular to the lever arm. So it's just, preference of notation. To be honest, I like this better, but the book uses this. So, all right, so anyway, so long story short, your net torque is going to be equal to some component of force times the length of the lever arm, right? Cool? And if we assume that's the only force, that force is equal to the mass times that tangential acceleration, right? And here's why they use tangential. It's accelerating tangentially. That means it's also accelerating angularly, right? So tangential acceleration is alpha r, using a jumper equation. Follow? All right, and then you can just regroup your parentheses, right, using what associated and commutative properties, right? And then mr squared is your I. Cool. And then if you had more than one particle, you would just be summing over all of these. It all works out. Okay. So one thing that I haven't commented on yet is this equation. When you use it, your alpha has to be measured in radians per second squared. All right. If you are ever unsure, always convert to radians. It's never wrong to convert to radians. Like that's always your safe bet. Okay. Often it doesn't matter, but if you're unsure, I would convert. Cool. All right, so I had a couple examples that I wanted to get, but I don't know that we have time for both of them. Let me do this. I think I'm going to jump to the second example, because I think the second example is probably more instructive. Although I'm worried that I won't have time for the second example. No, let's just do the first example, because I know we have time to get through it. All right, but so let me say this. Most of these problems boil down to the following two equations. In some sense, well, we just learned that torque is I alpha, right? Technically, net torque is I alpha, right? Okay? And we also know that for simple cases, your torque is you know, the length of your lever arm times your force, right? Maybe times a sine theta, right? So the way a lot of these problems are set up is you use one of these equations to find the net torque, and then you use the other equation to find some missing thing. So like maybe there will be a problem where I'll give you the force and the radius and the angle, and then ask you for the angular acceleration. You know what I mean? So you find your torque and then plug it into the other equation. So these two equations are kind of central to this whole chapter, and almost every problem goes through those two equations at the middle, like as a middle step, you know? Okay? All right, so, and that was why I wanted to jump to example 2, because example 2 is an example of that, but we don't have time for it. So, we even have time for example 1 now? I don't think we do. Nuts. Well, no, I told you guys we'd spend tomorrow going over questions and stuff. Finish it up? Tomorrow? I will do that when we get to angular momentum. All right, so I'm going to stop here, you guys. We don't have time. So tomorrow, come in with questions. I'm going to plow through these two examples, and then I'll answer questions. What did